This is probably the most clickbaity talk title ever. So my name is Jeethu, and I run a little optimized machine learning startup in Ireland. And I've been a part of Numerai since about 2016 as well. A lot has changed since then. Trying to optimize non-differentiable objectives is sort of an obsession of mine. And the other obsession is training neural networks. I think I've learned a lot of NMR using neural networks. Scoring functions on Numerai have almost always been non-differentiable. I think originally, when I first started, the scoring function was log loss, which was great, but it didn't last very long. And I think then they went on to use Spearman correlation, which is non-differentiable with the ranking. But you can, in some ways, use a relaxable approximation thing. So that was fine. And then we had TC. Took us a while to actually get used to it, and they told us to optimize for FNCV3. And this whole neutralization step, again, that makes it non-differentiable. So yeah, it's an age-old problem. I'm going to talk about three ideas around this. I think the last one's not very practical because I'm still building it. I just want to seed some ideas in people's minds, and maybe they'll take these ideas and run with them. So the first thing, start with what I do with the neural baseline that I have. Like I said, I like to train neural networks, and I hate trees. So essentially, I train a multi-task neural network on all targets, and I also train on validation. So that's that. You pre-train it with an eligible objective or something thereabouts, something very simple.
But why was the joke? Like, I never understood why the people like the training data is so old, also in signals. Like why do people even train on that? The market changes so much. It's like, and you said like I also train on validation, but it's for me it's more I also train on training data. That's stranger.
So the thing is, I think you should be open to training on anything. And also, I think Bob mentioned this, which is in some ways selecting the right errors to train on is somewhat of a thing.
There are some interesting birds in that area as well, right? So, and if you can train to avoid those, you still learn something.
So there are good errors in the training dataset as well, and there are good errors in the validation dataset.
My point is more if you had to choose, the more recent one should be the obvious choice ever.
So one of the things is they want you to train only on the training dataset, and they provide you the diagnostics tool to validate on the validation dataset. But it's so tempting. It's such a big dataset. Why waste it?
They also, I think this is the Pope thing, some of the example models are training on all the data. But in Prague, we should have something like the Numerai Anonymous, and so I'm Joseph, I'm training on all the data. I'm violating it all the time.
Also, I don't do any feature selection. So. The initial approach was you take this big neural network which has been trained on all targets and then fine-tune it on whatever the scoring target is. With experience, I found that it's usually a bad idea to do that. Turns out just the initial pre-training is good enough. And it's quite weird. So I think what actually happens is, even if you do hold out and things, training on a single target overfits. So it's quite a curious phenomenon. So now I have this neural network which predicts on 56 until recently, and then with the new thing it's 40 targets. But I only have to submit a single prediction. So the next thing to do is to essentially come up with a linear model, which essentially tries to ensemble these 40 predictions and use that to submit. While we're training a linear model, we might as well use some evolutionary methods and try to optimize for correlation or MMC or PMC or whatever it is. And yeah, so we use a gradient tree optimizer. I think there are like around a dozen packages in Python which can do this. I settled on this thing from Facebook called Nevergrant. It's a nice fun on not ever needing gradients. So it's a sort of a package which gives you about a dozen or so evolutionary optimizers. And the evolutionary field is actually quite big. There's this conference called Gecko, which is dedicated to the evolutionary algorithms and things. And so yeah, this specifically is essentially just a genetic algorithm, which is a tiny subset of the whole field. I think Bohr is more into genetic programming, right? Trying to come up with entire programs. Yeah, so Nevergrant is excellent. Scales across all your cores. If you have one of those AMD Threadrippers, it's excellent. So yeah, that is the evolutionary way. I think we'll move on to the next one now, which is this idea of using zero-thought optimizers. So the idea is we cannot compute gradients of these functions, but we can use this high school trick of finite difference. So you have a function, you add a small little epsilon to it, and you subtract a small little epsilon to it, and see how the output changes. And you can use that to compute pseudo gradients. And this is actually quite an old idea, like most ideas, but I think it's hot again thanks to LLMs. I think there was a paper from last called MISO. I think I have a slide with the algorithm. We'll talk about it. So yeah, the idea is to freeze the bigger neural network and train a small MLP with L2 loss pre-trained, and then fine-tune it with a non-differentiable objective with a zero-thought optimizer. Yeah, so it works reasonably all right. And like I said, it's a whole software itself. This is just one algorithm. There are dozens and dozens of different algorithms. So this is the MISO algorithm. The beauty of this is this was designed for LLMs. So one of the things is with regular gradient descent, if you're doing stochastic gradient descent, you need something in the order of, I think, 12x the number of, sorry, I think with SGE it's a little lesser. I don't quote me on this, but something in the order of 8 to 12x the number of parameters as optimizing parameters. So to train a 1 billion parameter LLM, you need something like 12 gigs of memory, or actually it's 24 gigs of memory because each parameter is 16 bytes, bits. So they use a very interesting trick where you can see random number generators and use that to recreate the previous state. So they just keep one copy of the weights and perturb it in one direction, perturb it twice in the opposite direction, and then perturb it back again. So you have the old weights back. And using the two loss values, you can compute a projected pseudo gradient. And then essentially just, this is standard Blackrock style stuff. You essentially subtract with the learning rate eta times projected gradients times z. Okay, I think z is just drawn from the number distribution. Yeah, so this is not on a break. The projected gradients are super noisy, so you have to keep the learning rate very low, which means learning is very slow, but it does work nominally. And yeah, it's definitely much more efficient than just brute force evolutionary optimization. So yeah, and also pre-training with a simpler gradient descent based loss helps a lot. Okay, yeah, so the final trick is essentially the idea of using a score function estimator. And this is, again, a very sort of provocative suggestion, which Moore already mentioned, which is Numerai perhaps isn't a supervised machine learning contest anymore. It's essentially a sort of portfolio optimization contest. Because one thing is the benchmark model from Numerai, and the other thing is you can always go buy stuff from Numerai. So you have good models already, and I think it's very hard to beat all of these good models. So it turns into a problem of picking good models. And so there's a conventional portfolio optimization based approach to do this. I'm just suggesting using reinforcement. I don't have this in production. I have some code around, but I think it should be in production pretty soon. So the idea is to use reinforce. This equation is from the reinforcement learning book. I think I have a reference on there. And so effectively, you have a reward. You discount it with alpha. GT is the reward at a given time step. And the idea is to maximize the reward. And reinforce is a policy gradient optimization algorithm, quite famous in the field of reinforcement learning. I believe it's also quite popular. I keep talking about LLMs because that's my data. So, the Google Gemma models were trained with reinforce. One problem with reinforce is high variance, which is not quite a problem with what we are doing here. And also it's extremely sample efficient, as all reinforcement learning is. So I have this simulation-based approach where, so the idea is that the neural network takes a state and predicts an action, which is which model to pick at a given point in time. And so what is state here? So state is essentially the mean return from a model, standard deviation, maybe a series of returns. I mean, it's essentially a feature engineering problem. And then it just predicts which one to pick. There's not enough real-world data to actually train a small little neural network to do this. So you essentially create a lot of fake data and you just train the network to do that. I have very high expectations for this. I don't know if they'll pan out, but we'll see. And also the beauty of reinforce is that your reward function does not have to be differential. So, and thus it neatly fits this whole and like I said, it's still work in progress. I think that's it. Yeah. Any questions?
So the last one is really interesting because I had always the kind of intuition that the reinforcement learning will be doing well. I have started about 3 months ago with that on unrelated things, and my conclusion after 3 months: this is dark art. It's working so weirdly, so many hyperparameters it's difficult. It's difficult. I started with a very simple game, completely lost. Some time ago, about the April Fools, I was publishing on Discord the reinforcement learning model applied for the stock trading. Was working very well, but of course it was a kind of desperate move. So I made it in 1 day, and there is a lot of bad things inside. But Jeffrey Devine actually contacted me. Yeah. And he said, I'm thinking in the same direction. And he pointed out some of the mistakes I made on the...
What algorithm did you use?
PPO.
PPO?
Yeah.
It's pretty...
PPO?
Proximal policy.
Yeah, proximal policy optimization. This is, I was basically, when starting, I was going for selection of the good library, and there is from OpenAI, there is stable baseline collection of the various reinforcement learning libraries. So I basically choose them. And also this is depending on your environment, because you basically need to train it into simulated environment, and that's the kind of issue for itself as well. So, but when I was going through there was one nice area. So because it depends also on how you define your reward function, value function, and a lot of the things which is really very difficult to establish. So I found one guy who was training the simple game of Snake, and he had the reward function very punishing. So when there was a bad move, there was a big penalty for it. So what the snake learned through reinforced learning was to kill himself immediately. Because the life was so much punishing that he just decided to kill himself, for that. So and these are many unexpected results. Like one of the examples, the guy was training basically that traditional way of walking of the guy. So the simulated model of the physical person, and then trying to run him for that. And what the model learned is just the fastest way was rowing, moving forward. There's so many variables into the it's really very hard. But I believe this is attractive. This is exactly the way.
So in some ways, I mean, reinforcement learning is a huge field, and PPO is by far the most complex reinforcement learning algorithm that I'm aware of. There are many simpler ways to look at it. I mean, one of the reasons why I'm such a fan of reinforcement is because it's such a simple algorithm, right? I mean, it's probably 20 lines of code if you implement it. And it normally works. But you're right about this thing about, it's very hard to get working. Yes. I mean, it looks so elegant and beautiful on paper, but in practice, it's a dark art. Yeah.
Could you go back to the formula?
This one?
Yeah.
Okay.
So I understood you're using theta as the parameters for the...
Yeah, the theta is the unit parameters. So, I mean,
so
I should have probably just had some Python code. It's so much simpler to read.
Okay, you have policy optimization algorithm. Theta is what you're after for your model. The states and actions, I did not really get how you use those.
So essentially, the neural network architecture is quite straightforward. It's an MLP, and the output is a softmax with a number of models that you're trying to pick. I mean, obviously, you can always have an extra option where you say, all things are so bad that I don't want to pick anything else, anything at all. But what I'm doing is just, I have K models, and I want to pick one of them. And scale is some notion of past performance for each model, because that's the state of the world. And so your agent, which is this neural network, given a state, decides on the next best action to take. So to train it, what you do is, given a certain state, train it with every single action. So you create the Cartesian product of all states and all actions, and then you train on that, and that's how it works.
So the state is the model. Yeah.
So the model is the agent. The state is the input to the model.
What I'm struggling with is where's the sequential nature of this? The snake is a good example. Yeah, you get into a state, and then there's only a few other states you can reach from this state.
You select the models, you run them, and then you have a state, and which is the result of that. Yeah, you look on that, and then you select another models, and then you have the next
step. You perform an action, and at the next step, the state may or may not update. You don't know, but that's how it's better.
Yeah, but in your case, in this special case, so you're after an ensemble, you want to get the parameters of your MLP. It's very simple MLP.
Right.
So where's the sequential nature in that? How does it matter?
So in this case, it's not a sequential game. All we're trying to do is maximize the expected reward. Right.
Yeah.
So given this state,
so
I want to pick the option. Yeah, exactly.
It's a one step.
Yeah.
So this should make it very easy. You don't need reinforcement learning for that.
There's
No,
some,
but there might be something in the reinforced learning which is making it really working.
I mean, you can always,
Yeah.
what you're talking about is Schmidt-Huber's idea of upside down reinforcement learning. Has anybody heard of it? Okay, so the idea is like, why the hell do you want to struggle with reinforcement learning? Why can't you just say, okay, you know what? Here's a state, there's an action. Give me the action which gives me the maximum rewards.
Yeah.
Right? So instead of actually predicting action, we try to predict rewards. And this is upside down.
And that's
yeah.
Because in reinforcement learning, you always want to, you don't want to optimize for the reward, you want to optimize for all the rewards you will get in the future.
So
This
cumulative
part-
rewards over time is what you're optimizing
Right,
for.
so you have a sum there of
Yeah,
rewards,
yeah.
and you want to optimize the sum,
Yeah.
not the reward.
So I think I should have probably added a term that GT is the sum of all past rewards and things, but I did not. And also I'm not doing it personally. So yeah, so it is essentially a discounted sum of past rewards, where the further back the rewards are, the less relevant it is.
But I think this is a really good point because, and this is the struggle of the kind of concepts or frameworks, because the optimum would be, for example, having the fantastic model for Numerai, whatever it would be, the neural network, and it would be perfect, So this is the solution of the problem, but you are not able to find it. We are not able to find it. So solution might be in looking for it, and this is something different. This is like
Yes.
you just the reverse problem. You just cannot find the optimal function for it.
But what you care about is only the optimal model, yes? So let's say it exists and you can stepwise find it, then you're not optimizing the sum of all the models you had.
So you're not optimizing the past,
It's
right?
not the cumulative sum, you're optimizing. Of course, there are iterative models to find a solution, and they are great. But for this, I think you don't need reinforcement learning because you don't care about the reward of your last model.
By the way, I was not able to find a use for the reinforcement learning, so this is the first time I see it. I thought that it would be useful for the signals, where I have kind of better way how I would be, projecting the next step, which would be the prediction for that. But this is the different usage and very interesting.
So I will post a link to the reinforcement learning book. I think it might make sense to look at the chapter on policy grading methods.
I read the books.
Oh,
but one thing this would really be interesting is staking. Yeah? There you have this temporal effect. Yeah? If I unstake something, I cannot earn on this, and my stake will be different in the next step. And you actually care about all the rewards you made in the past. So
yeah.
maybe.
Also,
maybe
since you
it's
mentioned
but imagine defining the value function. That's really hard.
yeah, maybe you don't need it.
So since you mentioned temporal methods, I think it's also worth looking into TD learning, right? Temporal difference methods. Actually, extremely simple. So you can just have one step, where you just look at the previous step and this step.
Yeah. Let's continue the discussion in the break. I like reinforcement learning a lot. I spent a lot of time with that when I was at university. So I'm happy to discuss that.
Sounds good.
But another question, all in the beginning is that you train on everything and everything. How long does it take?
Not very long. I think in the order of a few hours. I have a dual GPU machine, 23090s. So I think usually it's done in about 20 to 24 plus stops. I use early stopping, so yeah.
Yeah. And it might run hell of a lot of time.
Yeah.
Because you stop it, but
So-
you are not quite sure that this is the right model.
It is probably not a good idea to do early stopping, right? Given the phenomenon of double descent and things like that. Ideally, you want to continue for as long and then just pick the best one after a really long time.
The trading agent which I was publishing on the Kaggle on that was kind of doing the bad, so I trained it longer and it was started working well.
Also, I think there's so much you can do in terms of just the architecture of the neural network, things like that. So I haven't even gone into it.
Yeah.
I'm just thinking of the platform.
Yeah.
Okay.
Thank you.